Everybody, welcome back to the rest of our discussion on how to use the definite integral in the business and the economic world. So, let's start talking about income streams. What is an income stream? Well, as a firm generates income, it's very common for them to take that income and reinvest it because then they can get, well, their income plus interest on that income, and that's known as an interest stream. Formally, the accumulated or total future interest stream over a time period is the amount of money that the firm ends up making over that time period. And that's, of course, using that kind of aforementioned practice of you're making your income already and then you reinvest to get interest. So, if we let R of t, capital R of t, be our rate of income generation. At time t. Now, when we do our work for this section, R of t will be a constant for what we do, but it could be any function that you want. It's just that the resulting integrals require techniques that we aren't going to discuss in order to compute. But it could be anything you want, like the math is capable of handling that. For our purposes, we'll end up with R of t being constant. Alright, so if we let R of t be the rate of income generation at time t, lowercase r be the interest rate, and we'll assume continuous compounding. Again, the math is capable of handling discrete compounding, but it takes on a slightly more complicated form. So we'll just assume continuously compounded interest. And then we'll let t be the time period. Or rather the term of time that we're working with. So I'll skip the derivation here because it's kind of long and nasty. Your book discusses it, but using the fact that compound interest normally has the formula, continuously compound interest has that formula A equals P e to the RT, where P is principal. You can merge that with some knowledge of Riemann sums to end up showing that the accumulated / total future value after t years of an income stream of R of t dollars per year. Earning interest at the rate of R per year. And also compounded continuously. Also, please notice, everything is in terms of years. As long you can shift that as long as you shift all of them, right? Months, 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 days, days, days. Or you could shift dollars, should be whatever, freely, right? As long as you make sure to keep track of all your units, keep that all parallel, this all works. Compounded continuously is given by, so, what we're getting is this accumulated total future value. This is just some setup saying it's after t years, income stream is R of t dollars per year, interest is lowercase r, right? So like 4%, something like that. And it's continuously compounded. And it's given by the formula A is equal, where A is just our amount, the accumulated interest, or not interest, accumulated value, is e to the r capital T times the integral from 0 to capital T of r of lowercase t e to the negative r lowercase t dt. So, as I said, your book derives this formula using Riemann sums and the formula for continuously compounded interest. I don't expect you guys to know or be able to do that, just be able to apply this formula here. So what this is saying is, hey, if you're following that kind of business practice where you take your money, reinvest it, you make an interest stream, how much value do you get over the course of that time? This, right? This would be the final amount you would end up with in the account. Alright? So it's basically one way of measuring how good an income stream is by working with this. And you can make predictions where you say, well, if we follow this business practice, we assume that we'll get interest at this rate, and we'll have an income generation of this. So it's a good predictive model. Another good predictive model might be trying to find, okay, what if I just want to figure out, like, basically where the interest stream is doing, how it's doing right now at a given point in time. The present value, another long thing to write here, the present value of an income stream of R of t dollars per year over a term of t years earning interest at the rate of R per year, compounded continuously. So again, whole big long definition. All this is saying is, hey, you have the present value of this income stream. Here's the details about that income stream. And we've defined the present value of this income stream to be the principal P. So not quite the same idea as this whole thing, but similar formulas. It's going to be the principal P that would yield the same accumulated value. As the income stream itself. Were P invested for T years under the same interest scheme. So basically, if the interest was still being compounded continuously at a rate of R. So what is this definition here? It's looking for saying, hey, we know how much money the income stream will accumulate. But we're going to find a way of measuring, okay, how good is this income stream at this time, as being the principal we would have had to just put in as normal compound interest if we wanted to get the same amount of money at the end of the whole thing. So what does our formula for that become? Well, really what we're doing is we're saying, hey, how much will we get with just compound interest with this principal for T years? Well, we'd have P e to the R capital T power. And we're setting it equal to the amount that we would get from the income stream, which is e to the RT times the integral from 0 to t of capital R of t e to the minus little r little t dt. We're saying, hey, we are going to define P such that these two things are equal to each other. So we're getting P, we're not given P, we're getting P. And, well, if I want to get P, I might as well just divide both sides by e to the r capital T, and that'll cancel that away. So you're just left with our present value is the P, and it's equal to the integral from 0 to t of r of t e to the negative little r little t dt. Alright, so that's kind of a key thing to realize. This is different from just a compound interest problem, because in a compound interest problem, typically you'd be like given the principal and you'd be told, oh, how much money do you get at the end? Here, you're given this income stream setup. So you're given basically everything above there, and you're trying to find present value as a way of measuring, okay, how good is this income stream actually? So let's do an example. So this was our present value formula. Our accumulated interest formula was e to the r capital T integral from 0 capital T, r of little t, e to the little negative little r little t dt. Sorry guys, a lot of writing in this section. And there's only going to be more. Alright. Let's say a company is expected to generate $60,000 per year of revenue. T years from now. For the next 8 years. Alright, if the income is reinvested, so we're setting up our interest, or our income stream. If the income is reinvested, and earns interest at 6% per year, compounded continuously. Then we want to find the total accumulated rate of, well, this income stream. At the end of the 8 years. As long as we think our model is good for it, let's find it at the end of that. Let's also find the present value of the income stream after 3 years and 8 years. All right, whole big chunk of words right there. Let's start doing the math for it. All right, so let's write out what we know about our income streams setup. We're expected to generate $60,000 per year, T years from now. In other words, R of T is equal to a constant 60,000, right? You could make this a function of T, and then that would get you a variable R of T, but we're not going to be working with that practically. And for a lot of real-world applications, you don't need to. But once you do, there's more sophisticated integration techniques that can... It's the exact same formula, it's just you need more sophisticated integration techniques to actually take care of the problem. Alright, so we know that capital R of T is 60,000. Our little r is 0.06, right? We have this 6%. And our capital T is 8. Now, this is for the find the total thing at the end of 8 years. So we're working with that right now. Let's say T1 is 8, and then for this one we'll say T2 is 3. Alright, so that's our setup, that's all the pieces of information we need. Now we just plug directly into the formula. The amount is e to the r, so e to the 0.06 times capital T, T1 in this case. So let's say the amount at 8. Now, trying to figure out my notation here. Let's say total, right, for the total accumulated interest. In that case, A will equal e to the 0.06 times 8 times the integral from 0 to 8 of 60,000 e to the negative 0.06 t dt, which is equal to what? 60,000 e to the 0.48 times the integral from 0 to 8 of e to the negative 0.06 t dt. You can run your U sub, you can do whatever you want. If you just evaluate this integral straight, it ended up being 60,000 e to the 0.48 times e to the negative 0.06 t. Yes, it is negative. Yes, negative 0.06 t divided by negative 0.06. All right, and that goes from t equals 0 to 8. You could have also done a u sub, and that would have worked too. You would have had like e to the u divided by negative 0.06, and then it would go from 0 to some negative number, and that would have also worked perfectly well. Excuse me. And if you run that through your calculator, making sure it's the one with the 8 minus the one with the 0. So let's do one more step without the calculator. It'd be 60,000 e to the 0.48 times e to the negative 0.48 divided by negative 0.06 plus, right, you're going to have minus a negative. So plus e to the 0th, which is 1, divided by 0.06. You might be like, why is there a negative sign here if this is supposed to give me like a positive amount to the end? Because this part is going to overweigh that part. So don't worry about this negative sign there. That's meant to be there. That's all I need. Plug that into a calculator, and you would end up with roughly $616,074.40. And of course, there's more computation. You could do the 60,000 will start canceling nicely with those things in there, and then that 0.48 and that 0.48 multiplied to make 1, and then you'd just be left with a single 0.48. Anyways, there's nicer algebra you could do if you wanted to leave this symbolic, and it would all work out nicely. But if you run it through a calculator, this is the number you would get. So basically, this is saying, hey, how much money will your income stream actually generate over the course of these 8 years? $616,074.40, roughly. And that makes sense, because just from our income alone, we're expecting $60,000 per year for 8 years. So that'd be $480,000 right there. And then this is saying, hey, you get an extra $130,000 in interest by doing this streaming technique. So very useful streaming, especially because 6% isn't even that high of an interest rate. So very powerful tool for a company. All right, I'm going to erase on this side so we can leave our setup. So yeah, make sure you have all this down. Let's handle the second half of this question, the present value of the income stream at 3 years and 8 years. So our present value at T2 at the 3-year marker is going to be equal, we don't even need to do a colon, we can just say that this will be equal to, by our formula, the integral from 0 to 3 of 60,000 e to negative 0.06 t dt. And I'll do this one with the u sub so you can see the integral done both ways. If you did the u sub, u is equal to negative 0.06 t, then du would be negative 0.06 d t, which would mean we have the 6, so this is really integral from 0 to 3 of 60,000 divided by negative 0.06 times negative 0.06 e to the negative 0.06 t dt. Pulling that constant out, you add on 2 extra zeros, so you'd have 1, 2, 3, 4, 5, 6. So you have negative 1 million, times the integral from, okay, our new lower and upper bounds. If you plugged in 0 into here, you'd get 0. If you plugged in 3 into here, you'd have negative 0.18 e to the u d. Alright, so for our integral, you could either do it the first way that I did, where I didn't bother running through a u sub, I just used my differentiation, rules to my advantage, and that would work out fine. If you weren't comfortable with me using that method of integration, this one is for you. This is the exact same u sub that would work out the exact same. You'd have just an extra multiplication out in front. And you'd end up with this thing. I don't like having a negative above a 0 in my bounds of integration. I can swap those at the price of changing that negative to a positive. This is positive 1 million times the integral from negative 0.18 to 0 e to the u, which is 1 million times e to the u, going from negative 0.180. Plug that into a calculator, you'll end up with $164,729.79, give or take. Alright, so what is this saying? This is saying that if you wanted to start investing now, and you want to match where the income stream was in 3 years, then you would have had to have invested $164,000 of interest, and then it would compound to the same place as the interest after that time. All right, how about the present value at T1 after 8 years? Okay, well this is saying how much would you have to invest to match where the income stream is at the very end of its life. So we're expecting a bigger number, right? Because we're trying to match an extra 5 years also of accumulated income. All that changes about our problem is all these integrals, instead of being from 0 to 3, are now from 0, 8, meaning this bound as well is going to change. If you plug in 8 into here, you'd have negative 0.48. So that's where that number came from. And we'd again get 1 million times e to the u as u runs from negative 0.48 to 0. And you would plug that into a calculator and you would get $381,216.61. Alright, all this is straight up applying the formula. The first one I did without the u sub just because the u sub would have been kind of clunky, but here you see it with the u sub so you can see it either way. Alright, that's enough of the income streams thing for now. Really the key thing is saying, hey, once I have the problem set up properly, evaluating an integral is evaluating an integral. Spend enough time with it, do the proper u sub. It'll eventually work its way out. It might not be easy, but we can do it. We know how to do it. As long as we know how to set up the problem properly. Which is saying, hey, figure out what your income stream is, figure out what your interest rate is, and figure out what your T is. Those are the kind of key parts of this. Alright, let's talk about another popular business thing. Annuities. And if you're like me and you didn't know what an annuity was before, now? Annuities, don't worry, I know what they are now. Annuities are sequences of payments made at regular intervals. Over a given time period. Which we call the term of the annuity. even if you didn't know the formal definition of an annuity before then, which you probably do, having been in business, it's still not that complicated of a mathematical object to be working with. It's just saying, hey, every month you pay 20 bucks, or however much you choose to pay that month. You're just paying at regular time intervals for a certain amount of time. Makes sense. All right? So, technically, you can pay however much you want. I could pay $20 month one, $40 month two, $60 month three. And that's a valid setup for an annuity. Mathematically, those are more complicated types of annuities to work with. Can theory handle it? Yes. But we're going to make a normalizing assumption. Which is that payments are equal in size. And for a lot of really important applications, payments just are equal in size because that's how humans have set it up. So even though this does remove some of the generality of our work, it still leaves it applying to a broad swath of things that we consider important. All right, definition. How much money is in your annuity? The amount of an annuity is the sum of the payments and the interest earned. So in some sense, we've set up an income stream where we're getting payments and then there's being an investment made on those interests coming back, and we're saying, oh, we want all of that. So this is just an interest stream, meaning we can do interest stream things to it and get some nice formulas regarding annuities. All right, so if we let capital P, now instead of principal, it's going to be the size of our payments. Think, oh, I'm paying $20 a month here. And we let R be our interest rate, compounded continuously. Capital P, or capital T be the term of the annuity. And little m be the number of payments per year. Given this setup, annuities form an income stream of how much, well, set up an income stream, you need an RFT. What's RFT? RFT is going to be the number of payments per year times the size of each payment, MP. And here's where the normalizing assumption that payments are equal in size comes into play, because otherwise instead of M times P, you would have the sum of all of your payments, but it would get weird. You'd have M times P dollars per year with an interest rate of R. Over term capital T. So the interest rate and the term for the annuity transfer directly to your interest rate and term for your income stream. And then R of T comes from the other two quantities, this M and this P. All right, so we can now derive a formula for the amount in annuity. If we let A be our final amount, well, it's the amount in the annuity is just going to be the accumulated value of our interest stream. So it's equal to e to the r times capital T times the integral from 0 to t of our r of t, which is m times p, e to the negative r little t dt. Sweet. And now we can just start working from here. I'll put in full gory detail. This is equal to pulling out the MP, m times capital P e to the little r capital T times the integral from 0 to capital T of e to the negative rt dt. If I wanted to make the use of u is equal to negative rt, then du would be negative r dt, so I'm missing my negative r. In order to put it in there, I'll just multiply. It's negative r 1 over r times negative r e to the negative rt, which equals negative mp over r e to the r capital T integral from 0 to capital T of negative r, oh, there's dt there, e to the negative rt little t dt. Alright, let's hit it with our u sub. We need to remember to change the bounds, so our new lower bound is negative r times 0, which is still 0. Our new upper bound is negative r times capital T. So now this is the integral from, this is negative mp over r e to the rt, capital T, times the integral from 0 to negative r capital T e to the u du. Integrate, and you have negative m capital P over r e to the r capital T times e to the u as u runs from 0 to negative r t. Which, if you just keep going a little bit further with it, promise it sorts out even more nicely at the end. Negative m times capital P divided by little r e to the little r capital T times e to the negative r capital T minus e to the 0th. Which is equal to, I'm just going to group some terms real fast to make things easy. We have mp over little r times negative e to the little r capital T times, what's this? Well, this is 1 right here, and this is negative rt still. So we have e to the negative rt minus 1. Multiplying this in, this e to the rt term in, we end up with mp divided by r times negative, okay, multiplying these two together, e to the rt times e to the negative rt, those cancel, you just get 1. So we have negative 1 plus e to the r capital T. And that's our formula for the annuity amount. Just rearranging this slightly, mp divided by r times e to the r capital T minus. Alright, so messy kind of derivation, applying our compound interest formula, mostly just because the U sub is kind of eh. But you do the work and you end up with a nice clean formula for the amount of an annuity. And the key thing is, this is a formula involving only algebraic operations, and all of calculus has already been taken care of. So that's pretty nifty. Because, yeah, if you just have a normal interest stream, you don't necessarily get that because you don't necessarily know your R of t. But, yeah, it's pretty nice. I guess you could do it for any constant R of t without, but yeah. So, for an example, let's suppose you deposited $3,000 into an IRA that pays interest at 4% per year, compounded continuously. All interest in this section is compounded continuously. And then let's say you continue to deposit into the IRA. You then continue to deposit $600 twice a year for 20 years. How much is in the IRA after 20 years? So, this is an annuity. Using our previous setup for annuities, it's an annuity with our payment, our constant payment, being $600. Right? We're setting it up with our $600. And then we have, let's see here. Give me half a second. Sorry, I made the problem more complicated than it needed to be. This $3,000 is going to go back to being $600 as well. After consulting with my notes, I was like, wait, not sure this problem works quite as I thought it did. Because the whole point of an annuity is it's a constant payment each time, or at least that's the assumption we've made. Alright, so you deposited $600 at 4% interest, and then you keep depositing $600 twice a year. So this is an annuity with our payment amount being $600, M, right, our number of payments per year being 2, paying every 6 months. And our interest rate is 4%, 0.04, and our time period T is equal to 20 years. So I haven't worked out the numbers for this, hopefully it goes. The amount in our annuity after 20 years, so the answer we want, is according to our formula here, 600 times 2 divided by 0.04 times e to the 0.04 times 20 minus 1. Alright, so this is 1200 divided by 0.04 times e to the 0.8 minus 1. Doing that division out, that's 300 divided by 0.01. So add 2 zeros on, we get $30,000 times e to the 0.8 minus 1. Alright, and if you were to run that through a calculator, let me just get out mine. Let's see, 0.8, and then I need e to that, minus 1 times 30,000. You'd end up with roughly $36,766.23 in your IRA. Pretty good for after 20 years. All right, let's move on to another example. All right. Yeah, there we go. Before our next example, let's also note, just like we have a total value for our annuity corresponding to an accumulated amount for an income stream, we can do the same with the present value. And we can say that the present value of an annuity it's the exact same derivation as the one for a total value, so I won't redo it. The only real difference is you aren't multiplying by e to the negative rt in the front. And for that reason, you're going to get that the present value will be mp divided by r times 1 minus e to the negative rt at the end. So an example of this would be, say a business owner wants to establish a slush fund, rainy day. I'm pretty sure that's what a slush fund is. From which they will withdraw $500 per month, and notice that's per month, for the next 5 years. Basically, they're saying, hey, we know we're going to need this money, so we're going to set it aside for now and let it earn interest while we wait to use it. And if they set this up with a fund earning interest at 6% per year, compounded continuously, of course, how much money is necessary to establish the fund? So what this does is it allows us to see how much this interest is really working for us. Because if I were to just set aside the money and bury it in the ground, right, not get any interest from it at all, then I'd need, okay, $500 per month is 500 times 12 is $6,000 per year for the next 5 years, so I'd need to set aside $30,000 to make this all work. But if we use our present value of an annuity formula, essentially saying, hey, you have this annuity already set up and you're taking away from it. So it's an annuity with P equal to $500. That's the amount essentially you're taking out of it. In M of 12, because we're working 12 months in a year. Let's see here. P is $500, M is 12, interest rate is 6%. And our time period is 5 years. So now we have all the information necessary to plug into our formula. So what would we get? Our amount that we need to establish the fund is 12 times $500 divided by 0.06 times 1 minus e to the negative 0.06 times 5. Start doing the arithmetic there, and you're going to end up with $6,000 divided by 0.06 times 1 minus e to the negative 0.3. Doing that division, you'll end up with $100,000 times 1 minus e to the negative 0.3. Run that through a calculator, like I'm about to. 0.3 negative e2 plus 1. You'll end up with $174,000 or $174,081.82. Is that right, or did I carry a decimal? Nope. Let me double check my math real fast. I'll be right back. Yep, I plugged into my calculator wrong. I didn't write this minus sign. Silly me. All right, it ends up being $25,000. $25,918.18. I was like, this should have been a number less than 30,000. That's what we talked about earlier. All right, so yeah, going back to that, we would have needed $30,000 just set aside to have this amount of money. But because we do it in this annuity way, because we set it aside in a fund that earns interest, now we only need $25,900-ish. So suddenly I've saved $4,000, which is pretty consequential over the course of things. All right, so that's kind of our examples for annuities. Let's handle one final topic that definite integration is good for business. You could go on about things for quite a while. So the question is, well, what is good for us to handle? And your book has decided a few things. Let's talk about income distributions. All right, so definite integrals are going to be used to study how income is distributed in a society. So how are we going to do that? We're going to let f of x be what's known as a Lorenz curve. You say, what's a Lorenz curve? Well, a Lorenz curve is a curve that measures how income is distributed. So that is, let f of x be a function denoting the proportion of total income of the population received by the poorest 10%, or by not the poorest 10%, the poorest 100x percent of the population. So that's kind of an abstract definition. I think an example would help. If we had some function f(x), so there's not a single unique Lorenz curve. There's multiple Lorenz curves. But for a given one, we had f of 0.4 equal to 0.2. That would imply that the poorest 40% of the population, so if we plug in x, right, the poorest 100x, 0.4 times 100 is 40. So the poorest 40% of the population would receive 20% of the total income. Right, that's what it means. If you plug in a percentage of the population, you'll get back a percent of the wealth that they actually are getting. Alright, so I said that there's a bunch of different Lorenz curves. In fact, there's infinitely many different Lorenz curves because it all depends on how your society's income distribution is set up. What are some properties that all of them are going to share? Well, for starters, each of them is going to have a domain of 0 to 1. Doesn't make sense for me to plug in less than 0% of the population. It doesn't make sense for me to plug in more than 100%. They're each also going to have a range of 0 to 1. Right? 0% of the population will have 0% of the income, and 100% of the population has to have 100% of the income, right? Because everybody's there, that's all the income that can be had. Sorry, we should say range F. Alright, so the domain and range are both 0 to 1. Third property, as I stated, f of 0 is equal to 0, and f of 1 is equal to 1. 0% of the population has 0% of the income, 100% of the population has 100% of the income. Next, f of x is going to be less than or equal to x for every x in the domain. Okay, why is that? Well, because if the poorest, say, 50% of the population had more than 50% of wealth, then they wouldn't be the poorest 50% of the population. So we get this property. f of x is less than or equal to x for everything in the interval. And finally, f is increasing on 0, which makes sense, right? You can't have more people and suddenly have less money held between them. Alright, so a general shape for a Lorenz curve would look something like, here's 1, there's 1, you get a point there at 1, 1, you get a point there at 0, 0, and it's going to look something like this in between, where this is the line y equals x. So that's generally what the Lorenz curve looks like. And again, we're working in this domain and range. So basically we have a box. We cut the box in half using the line y equals x. Right? right? This thing, and then we draw some curve below it that just connects those two dots continuously and never goes down. All right, well, what would the income of a society with perfect wealth distribution look like? It's not perfect in that, oh, everybody has the same thing, but if everybody had their share of income, percentage-wise, what would that look like? Well, it would look like the line y equals x. If the poorest 100x% of a society had 100x% of the income, right? Because they'll always have less than or equal to this much, but if they had as much as they should, so this is an evenly distributed, equitable society. The Lorenz curve would be f of x equals x. So we call this the line of complete equality. Why is this line of complete equality? Because for every person you add, you're adding the same amount of wealth. So, equitable society. All right, well, clearly not all Lorenz curves are this line, right? They just have these properties, but they aren't necessarily all this line. Here's one right here. But the closer that Lorenz curve gets to that line, so maybe we have this Lorenz curve, and we have another one in between them, and maybe another one that's even closer to the line, right? The closer a Lorenz curve gets to this y equals x line, the more equitable, the more fair the society is. So we can actually measure how unfair a society is by measuring how far away their Lorenz curve is to this line. All right, well, how do we mathematically measure that? It's not like I should get a ruler out. That's probably not a great way to do it. But what can we do? Well, we can leverage the area between the curves here. Because if this line is getting really, really close to this line, then the area between them is shrinking down to nothing. So what we do, sensibly, it should make sense to give it like a coefficient between 0 and 1, where it's like 0 is you're 100% fair and 1 is you're 100% inequitable. So we'll define the coefficient of inequity which is also known as the Gini index. So it's going to be the coefficient for a given Lorenz curve, which represents a given society. And it's going to be the ratio of the area between the line of complete equality and the Lorenz curve. So if I were to erase all this here, make another sketch. Here's our line of complete equality. If we make our Lorenz curve like this, we're saying, hey, take this area in between them, and we're going to take the ratio of that thing and the area, or the ratio of that thing to that of the area under the line of complete equality. So in other words, this divided by that area right there. But we know how to find both of these areas. This is a triangle with base 1 and height 1. So that has area 1/2. And this we can use our technique for area between two curves. This is the integral from 0 to 1 of x minus f of x dx, right? Since we're going between 0 and 1 and y equals x is on top. So our coefficient of inequalities formula ends up being, okay, divide by 1/2 is the same as multiplying by 2. So it's going to be 2 times the integral from 0 to 1 of x minus f of x dx. Okay, so this is our tool for measuring how unequally distributed a society can be. And when I say society, I mean anytime you can really group people together. Let's do a quick example, and then I think it's it. All right, making up the curves for these professions on the spot. I don't know if this is accurate or not, but let's say chainsaw jugglers have a Lorenz curve, or have an income Lorenz curve of f of x equal to 2/5 x squared plus 3/5 x. And what's another strange profession? Bear wrestlers. And bear wrestlers have a Lorenz, or an income Lorenz curve of g of x equal to 3/7 x to the 4th plus 4 over 7 x. All right, so we have our words. Sorry, we have our two professions. And we're saying, hey, the incomes are distributed according to these curves. Which profession has more equitable income distribution? And if you were to try to sketch these and be like, okay, can I just get a feel for the area? The curves wouldn't really help you because one of them is going to start and be further away from the line at the start, but then approach more rapidly, and the other is going to stay a longer distance away from the line for more time. So calculus is really the way to go because it means we don't have to guesswork anything. Alright, so what we're going to do is we're going to find the two coefficients of inequity and figure out which one is smaller, aka which one is more equitable. So, let's look up the chainsaw jugglers. The coefficient of inequality, which I'll just call the G index, because it's less, right? It's going to be the integral from, 2 times the integral from 0 to 1 of x minus 2/5 x squared plus 3/5 x dx, which is 2 times the integral from 0 to 1 of negative 2/5 x squared plus 2/5 x dx. Correct? Correct. Well, that worked out more nicely than I could have anticipated. Alright, pulling out the 2/5 from everything, you'd end up with 4/5 times negative integral from 0 to 1 of x squared dx plus the integral from 0 to 1 of x dx. So I pulled away a 2/5 from everything to the front, and then I split off the minus x squared here and the positive x using the sum rule. Applying the power rule now says this is 4/5 times negative x cubed over 3 as x goes from 0 to 1 plus x squared over 2 as x goes from 0 to 1, which is 4/5 times negative 1/3 minus 0/3 plus 1/2 minus 0/2. This is 4/5 times 1/2 minus 1/3 is 1/6. So we're going to end up with 4 over 30, or 2/15. So 2/15 is actually a pretty small number. That's like less than 0.2. Yes, less than 0.2. So who knew chainsaw jugglers were a pretty equitable society, I guess. How about that? Alright, let's do the other one. Bear wrestlers. Their index, or their coefficient of inequality, is 2 times the integral from 0 to 1 of x minus 3/7 x to the 4th plus 4/7 x dx, which is 2 times the integral from 0 to 1 of negative 3/7 x to the 4th minus 3/7 x dx. Again, worked out nicely. Guess because these are both x's, that's why that worked out the way it did. Alright, pulling away 3/7 and doing the exact same thing as over there really, we end up with 6/7 times negative integral from 0 to 1 of x to the 4th dx. Sorry, this should be plus right there. Plus the integral from 0 to 1 of x dx, which is 6/7 times negative x to the 5th divided by 5 from 0 to 1 plus x squared over 2 from 0 to 1. 6/7 times 1/2 minus 1/5 is what I'll end up giving you. And that's 6/7 times 1/2 minus 1/5 is, let's see here, 5/10 minus 2/10 is 3/10, which is 18 divided by 70, aka 9 divided by 35. And if you punch those two numbers into a calculator, I'll tell you right now that one's bigger, but 2 divided by 15 is roughly 0.13, or in fact it's equal to 0.13 repeating. And 9 divided by 35 is roughly 0.257. So, looks like the bear wrestlers are more inequitable than the chainsaw jugglers. So this is greater than 0.13. So chainsaw jugglers are more equitable. How progressive. In practice, you can use this to compare between different fields which have some other social quality you're interested in, and then you can use this as a comparison of how is that social factor influencing inequity within your group. All right, I think that's all for this video. It's dragged on long enough. This class's content is now done. So look over these videos, get ready for the final, and as always, feel free to come to office hours and ask me any questions that you have. See y'all on the other side.